the Smart Buildings Academy podcast with Phil Zito, episode 472. Hey folks, Phil Zito here, and welcome to the Smart Buildings Academy podcast. In this episode, we're going to be discussing airside systems, and we're going to be specifically talking about fan coil units, rooftop units, and if we have time, we will get to air handling units, specifically 100% outdoor air and mixed air units. I know my voice sounds a little scratchy. I hope you all had a great Thanksgiving. The entire family got sick, and we're all recovering from our colds. But other than that, it went pretty well. So as I mentioned in this episode, we will be going through those airside systems. This will be part 2 of, I believe, what will be an 8-part series on HVAC control sequences. So this is my Christmas, Hanukkah, I don't know, whatever holidays occur during this season. Those are the 2 I know of. But this is my gift to you all in us going through the most often misunderstood and most often poorly scored on section of our skill assessment, which is HVAC control sequences. So enjoy. You all been doing a great job of engaging in the comments and asking questions. Please do more of that. It really helps. And if you find this valuable, definitely go and subscribe on Apple Podcasts, Spotify, YouTube, and if you're listening to this on LinkedIn, please comment and share it. As always, everything will be available at podcast.smartbuildingsacademy.com/472. All right, folks, let's get into the episode. In this episode, we're going to be discussing airside units. So we're going to be talking about fan coils. We're going to be talking about rooftops. We're going to be talking about air handling units. We're going to be talking about pressurization, supply versus exhaust, volumetric offsets and matching. And we're going to dive deep into the topics of airside control. All right, so let's dive in. Airside control. Okay, so in episode 1, we talked about space control. We talked about individual zones. And we're still going to be talking about individual zones initially in this episode in the forms of fan coils and rooftop units. From there, we're going to go to multi-zone control. Now, multi-zone control is exactly what it sounds like, right? It's multiple zones that we're controlling. Before we even get there, though, we need to understand kind of what we're controlling and why we're controlling it. Now, as I discussed in part 1, our primary control is going to be air. We are most concerned with controlling air. It doesn't matter what temperature the air is. It doesn't matter the humidity level of the air. If we can't get the air to the right spot, then none of that stuff matters. So our primary focus point is making sure we have airflow. Now, within a building, if you've ever been inside a building, which, geez, I sure hope you have, inside a building, there's this concept called pressurization. If you've ever walked into an office building and the doors blow open as you start to open them, or they're already open, they're cracked open just a little bit, and you feel air whistling through, well, that is an overpressurized building. What that means is there's more air being pumped into the building than is being exhausted out of the building, and that air has to find a way out. If you picture air, and I think a lot of folks get this mixed up. They picture air as air, and they picture water as water, and they don't realize that they both have mass. And if you were to put water into a cup and keep filling that cup, it would overflow, right? Well, it's the same with air. If you keep putting air into a building and you fill that building up with air, eventually that air is going to find a way out of that building. And so that's called pressurization. Now, pressurization is really important for us to understand because it's how we control all of our zones. We need to make sure that we are delivering the right amount of air volume to a space in order to change the environmental variables within that space. And we do that by going and pressurizing the building. Typically, we will have a building be positive pressure, and the reason behind that is that we are keeping the hot air or cold air outside of the building, depending on the time of the season. And in spaces, we can have both negative or positive pressure. So some spaces we may not want whatever's in that space to get out. These are typically like isolation rooms. And so we will have a negative pressure. And in other spaces, we will want to keep stuff out, so we'll have positive pressure. So we do this with our airside units by modulating supply and exhaust fans. And a fan, quite simply, is a device that is driven by a motor, and it moves masses of air, depending on the fan type, using a variety of methods. And it will go and move air, and that air will then go down ductwork and will be delivered to diffusers, which then will allow the air out. Now, that's typically in fan coils and rooftops. In air handling systems like air handlers, especially VAV air handlers, the air will be delivered via the ductwork to a VAV box, which then will regulate it even more. Now, we're going to come back to that because there's some important things that have to happen in order for that to work. But before we do that, let's go through a fan coil. Now, what I don't have, I have every sequence here except for a fan coil sequence. But, I mean, I've got fan coil sequences fairly well memorized, so I can just take you through it even without having it directly in front of me. So a fan coil, the purpose of a fan coil is to have a individual zone system that can control a space independent of any other system. So it's like a rooftop, right? It's basically like a rooftop, except for typically it's going to be inside the building, and also typically it's zoned for a space where you want to have, really, you want the cooling source right there, and you'll see this in like IDFs typically. So data closets where you could have a high potential for heat and you want to keep a space cooled. And so you'll have this, this fan coil unit sitting right there. And a fan coil also a big, and I hesitate to say this because it's not always true, but most fan coils will just utilize plenum air for themselves and won't be using outside air. Now, I know as soon as I say that, I'm going to start getting messages from folks saying, well, I've got a fan coil that uses outside air. And you're absolutely right. There are fan coils that use outside air. But most of the time, when you need outside air for ASHRAE 62.1, you're going to be utilizing a rooftop unit. When you have a IDF or MDF space that is not persistently occupied and you're not terribly concerned with outdoor air quality because you're not bringing in outdoor air, you can typically use a fan coil and that'll be just fine. Fan coils also, most of the time, once again, this is one thing that I'm saying, most of the time, people, you guys and gals, you email me and I even say most of the time. I don't say absolute, so hey, you're hearing it. Most of the time, they are hydronic coils, so they are water coils. They're hot water coils, and they are chilled water coils. They'll have a condensate pan, and that condensate pan will allow the condensate to drip in it, and it'll have a float alarm, and if the condensate gets too high, meaning it's not draining, then it'll trip and it'll turn off the fan. But let's talk through the sequence. So essentially what will happen is the fan coil will look at the space temperature. Based on the space temperature, if it is above set point, the fan coil will go and drive the cooling valve to maintain supply or zone temperature, depending on setup. Now, typically, the fan is going to be running, but this isn't always. Sometimes the fan will only run when it's in cooling or heating mode. Sometimes the fan will be designed to run all the time. So it just depends on the sequence that the engineer set up. Okay, so you've got this fan coil, right? And it's running and the cooling comes on. And then once it meets set point, the cooling will close down and the heating can open up. And if it goes below set point, right? And so that's how it controls it. And it's got a little bit of deadband between the cooling and the heating set points. So you have two separate set points. And those set points are typically controlling the zone temp, but sometimes controlling to supply or discharge air, depending on what you want to call it. Personally, I like to call everything discharge air if it's being discharged, and I like supply air to be the incoming air, especially at VAV boxes from an air handler. It's more clear that way. Supply air is being supplied to a unit. Discharge air is being discharged from a unit. That's how I like to word things. That makes sense to me. As I mentioned as well, you have a condensate pan and you have a condensate alarm, potentially a condensate pump, and you will simply have the, so basically as the coil runs, right, as the cooling coil opens up, that cold air is going to hit it. It's going to reach saturation, right? If we're familiar with psychrometrics, it's going to hit that point at which saturation is achieved, 100% relative humidity, can't put any more moisture in the air. Air starts to wring out in the form of condensate. Condensate rolls down into the drain, drains out into a pan, which then drains out into another drain, and there you have it. You have your condensate, and if that pan starts to fill up, well, guess what? The float, that is the condensate alarm, will start to float up, it'll trip, and it will turn off the unit and generate an alarm. That's typically the sequence of fan coil units. Moving right along to rooftop units, we begin to see a very similar sequence, but not necessarily the exact same sequence. Let me get to it right here. Where'd it go? Single zone rooftop unit. And in this, it says a programmable thermostat controls the operation of the rooftop unit. Wow, that's amazing. Desired occupied and unoccupied heating and cooling set points are programmed via the thermostat. Okay, folks, if you're like having a mental lock on this and you're like, it's not using a thermostat, it's using controls. Okay, well, I'm going to help you out here. Replace programmable thermostat with controls. There you go. Thank you. All right. It's early in the morning. I'm a little sarcastic. But anywho, so we've got this programmable thermostat. And we've got this controls and the operation of the rooftop units being controlled by them. Then we have occupied and unoccupied heating and cooling set points. And they are programmed via the thermostat or the controller. And fan operation is determined by the position of the fan on auto switch. Okay? So on this fan, it has on or auto. Most of the time for us, we are going to be in auto mode. All right. And then the heating and cooling operation is described as heat, auto, cool, off. Most of the time, we are going to be in auto mode because we're controlling this with a building automation controller. So here's the big difference, right? With a single zone rooftop unit, most of the time, not always, but most of the time, these are considered packaged units. Everything's self-contained. It's all packaged together. And as a packaged unit, it has DX cooling, and it also has a typically gas heat. Okay, so DX cooling and gas heat. Now, what's going on here is that we're driving, once again, based on zone temperature. Okay, we're driving based on zone temperature. And this zone temperature is going to drive our heating and cooling. But we also have a supply fan, right? So if we talk through the unit, we have a heating and cooling system, typically direct expansion cooling, which is very similar to if you're familiar with chillers. We're using compressors, and we basically have a condenser and an evaporator side, and we remove the heat, and then that heat gets transferred to the refrigerant, and then the refrigerant then transfers that heat out of the airstream into the outside air. That's how compressors work, right? So we're removing the air from the building airstream and transferring it to the outside air. Basic direct expansion cooling. And then gas heat, I mean, right, we turn on the gas, we ignite it, it heats up, and then it heats the air. Gas heat, pretty straightforward. Electric heat, exact same. We introduce an electric signal across some wires that have resistance built into them. As we know, resistance causes heat because the electrons can't flow through. They start to heat up, and that creates heat. And so that is how we introduce heat as well. So you've got DX cooling, and you've got gas or electric heat on rooftop units. Additionally, we have a supply fan. Occasionally, we will have a outside air damper and return air damper. Sometimes we will only have an outside air damper. If we do, have an outside air and return air damper, they are normally interlocked and opposed. So meaning that if the outdoor air damper is 100% open, the return air damper is 0. If the return air damper is 100, the outdoor air damper is 0. So we kind of see how that works right there. All right, and we also tend to have a discharge air temp. Sometimes we will have some safeties in the form of static safeties, as well as low temperature safeties. There you have it. Those are all the points we have. So let's talk about the sequencing. Pretty much exactly the same as a fan coil, right? The fan might run all the time during occupied. It might only cycle on when we're in a heating or cooling mode. Typically what will happen is the outdoor air damper on the 100% outdoor air units will open up fully, but prior to engaging the fan, once the damper end switch is made to prove that we have the damper open, the fan command will be allowed to pass through that end switch electrically, and it'll energize the fan contactor and turn on the fan. Fan then runs, and then the unit will control to space temp. It will drive the heating or cooling either through staged control in the case of most electric except for SCR, and most DX, it will drive it sequenced on. So it'll be, hey, stage 1, stage 2, stage 3. In the case of gas, it will either turn it on, or if you modulate gas, it will go and modulate it. But typically gas is just on off as well. All right. And so you control temperature. Additionally, now we start to introduce this concept called economizer, which basically is a way of using outdoor air that is cold so that we don't have to cool down the air. Pretty nifty, right? Take advantage of that. It's also a way of using the outside air damper. Well, this isn't called economizing. This is called actual demand ventilation, where we open up the economizer to a point to allow the appropriate amount of air, fresh air in, so that our occupants aren't breathing CO2 and passing out, because we want them to have fresh air so that they stay awake and they get enough oxygen. So what we do here is that we go and we take our outdoor air temperature and we look at it. And there's a variety of different ways we can do this, okay? So I'm going to take you through a lot here. One of which is we look at the outdoor air temp versus the return air temp. And if the outdoor air temp is less than the return air temp, we will open up the economizer and let that outdoor air in, and we'll use that in lieu of the cooling coil to actually cool down the space. Now, there's a danger with doing that. Obviously, we're not factoring in humidity, so what we'll typically utilize in those kind of scenarios is actually enthalpy, which is a combination of temperature and humidity, and it actually gives us the energy amount in the air, because and I'm just picking numbers out of the air here. I'm not even looking at a psychrometric chart, so if I'm wrong with these numbers, I'm wrong, because I'm not looking at a psych chart. I want to preface that. But 80 degrees at 40% relative humidity is going to have less moisture in the air than 72 degrees at 90% humidity. I'm pretty sure that works out on a psych chart. I chose some extreme numbers there. So if we look at it from that perspective, it may be more efficient for us to use outdoor air than that return air and just bring in that fresh air. It may not. Depends on our set point, depends on a lot of variables. But those are two ways, right, of temperature as well as enthalpy comparisons in order to drive outdoor air damper enablement and to drive it to control. Now, outdoor air dampers also, they will either drive to control the discharge air temp, kind of like the cooling coil sequence. So you have a DX coil sequence. So you'll go and you'll drive the damper open and shut to control the temperature. Typically zone temp, sometimes discharge air, sometimes mixed air temp. It depends on the sequence. But you'll also have this other thing, which is outdoor air enable, where we ignore outdoor air versus return air. We ignore enthalpy, and we just look at straight outdoor air temp, and we say if we're above 65 degrees, we're going to enable the outdoor air damper to be open. Now, In climates that are relatively mild, not very humid, this can work well. This obviously would not work well in like Louisiana, where it's super humid. This would not be a good idea to use this strategy. So those are kind of ways of opening up the outdoor air damper. Additionally, we have CO2 control, which we will talk about in the air handling section, because you see it occasionally, but you don't see it as often. You don't see CO2 control in a rooftop unit. You typically will see that in an air handler. Although sometimes you see it in a rooftop unit if that rooftop unit is serving like a cafeteria or an auditorium, things like that. But those tend to be the cases. You don't tend to see it when an RTU is serving a classroom or something like that. Okay, so rooftop units. We talked about fans. We talked about our coils. We talked about our dampers. We talked about our set points. Now I'm going to read through some sequence language and just kind of help you understand some stuff. So, as I mentioned, we are going to go and control our rooftop unit based on achieving a set point, typically a room set point, and it's going to be an occupied and unoccupied, meaning occupied is occupied, unoccupied is unoccupied. I don't think I need to explain those. And we're going to go and say, okay, occupied is this, unoccupied set point is that, and we're going to control to those. But here's how the control happens, right? So if the outside air is not suitable for free cooling, as determined by the outside air dry bulb temperature, right? That's that regular temperature, or enthalpy. See, they say enthalpy, right? Then the outside air damper remains at the minimum position. This is for cooling mode. Minimum position. Why are we remaining at minimum position? Well, we're there because we need to provide that minimum outdoor airflow to satisfy ASHRAE 62.1. So from there, then the first stage of DX cooling is engaged. This is where we're using a sequencer block in our program, right? So up to this point, we have used a comparative pattern to determine if we're in cooling mode. We're driving that into a PID loop, which is feeding into a sequencer. And we also have a comparative pattern to enable our outdoor air damper. And we're taking a minimum select of whatever the minimum position is because we're not above or we're not suitable for free cooling. Okay, so upon a further rise in temperature above occupied cooling set point, then the second stage of cooling is engaged if the rooftop has two stages, and it just continues on and so forth. And then as the temperature falls back down, we disengage the stages in the reverse order of what they were turned on. So if stage 2 was the last one on, stage 2 is the first one off. And we have minimum on and off times in our compressor in staging. And we have minimum and maximum run times as well because we don't want to burn them out. So if the outdoor air is suitable for free cooling, right, as determined by those factors, then the outside air and return air dampers are going to modulate to maintain a discharge air temperature, typically of 55 degrees. When we talk about air handlers, we will talk about why 55 degrees. We'll talk about why that is used so often as the set point and what that means from a psychrometric perspective. Quite honestly, I'm looking at the timing on this episode and I'm like, man, we are not going to get to air handlers in this episode, which I'm okay with. I don't want to rush through air handlers and miss out on so much air handler goodness. So as I said, if the outside air dampers is good for free cooling, then we are going to go and turn on free cooling. And we're going to drive to a discharge air temperature or to a mixed air temperature or to zone temperature, whatever it is supposed to be driving to. If the outside air damper is fully open and still cannot satisfy the cooling needs of the space, then it will call for a second stage of cooling, which will be the first stage of DX cooling. And space temperature will fall back towards set point, and then the DX and the economizer will disengage and close down, right? I don't know how I feel about this sequence, to be quite honest. This assumes that your outdoor air enable is smart enough to know that, hey, I'm not going to have outdoor air economizer open when it's 90%. I could see how people could read this wrong and they would be like, oh, my outdoor air damper's open at 90% and both stages are cooling or on a meet in the sequence. No, not quite. So it's really important that you understand what is the low point, but as well as what is the high point for your economizer enable, because you don't want your economizer open when it's 90 degrees with 60% relative humidity outside and you're just bringing in hot, muggy air that there is no way your building's going to be able to remove that with your compressors, and you're just going to destroy your units. You're going to destroy the inside of your building. It's just not good. So I want you to really be aware of that, right? And then moving on to the heating portion, right? When the outdoor air damper, or when the space temperature drops below the occupied heating set point, the unit is put in heating mode. So the outdoor air damper remains at the minimum position and the first stage of heat is engaged. Upon further drop in temperature below the occupied set point, more stages of heat are engaged. And if you can't meet the heat or you can't meet the set point then you're either in a design day scenario or you have an undersized unit or you have some sort of mechanical issue going on. But this is often why you will see these kind of units actually paired up with perimeter heat like radiators, and those will actually form a heat curtain on the exterior side of the building to keep that heat loss from happening, that heat loss through the windows and things like that. And then you'll have the unit actually heating the air. Okay, I hope you enjoyed today's episode. I hope it was informative for you. I hope you are leaving with a better understanding of some of the types of airside systems that you're going to run into in the field. We're going to continue this series next week with part 3, where we're going to be going through the 100% outdoor air units as well as the mixed air units. And we're going to keep chugging along through this holiday season, giving you these gifts of control sequence podcasts. So as always, everything will be available at podcast.smartbuildingsacademy.com/472. Once again, that is podcast.smartbuildingsacademy.com/472. And I will leave you with this. If you are trying to figure out what your training schedule is going to be for your team, I know a lot of you are either just got done budgeting, or in final budgeting right now and final planning, and you're trying to figure out what are you going to train your team on. Use our free skill assessment. Go to smartbuildingsacademy.com/skills. Once again, that is smartbuildingsacademy.com/skills. Use that free skill assessment. Determine what gaps your team has, and we will be there to help you close those gaps once you figure out exactly what you need to work on for your